So we'll get to the question here shortly. Before we hit this up, you know, I have a soft spot in my heart for shopping carts. Did you know that?
I did not.
Yeah, it's, any idea why? They're just kind of in my heart. I feel bad for them, actually, quite a bit.
They get pushed around.
Yeah, those poor shopping carts. They just get pushed around all day long. Except for that one that's on the top of the snowbank across from Walmart. That one's having a good time. So, let's take a quick look at the question here. It's kind of a shark-themed day for me, so let's see if you guys can see this behind the shark there. That'll do. So we've got 150 meters from the ground to where the object's being released from. The person throws it down at 5 meters per second. The question is, how long does it take to reach the ground? So we're going to go through this together. Any idea on which equation we should start with here? The top one? That's a good idea, because let's take a look at the others. This equation right here, I'm looking for time. Time is not in there, so that's not going to be helpful at all. This equation here has time, which is wonderful, but I would need both of my velocities to make any use of it. All I have is the original velocity. I don't have the final velocity. So this is a good place to start. Move the shark for now. He'll be back, don't worry. So let's take a look at that long y equation and see if we can get to a solution. So we know the impact location. It has an impact spot. So what's the final height going to be equal to? 0. What is the original height? 150. And then we've got an original velocity. He's throwing it down at 5 meters per second. So what's the original velocity? -5, right on the money. And then we've got 1/2 at squared. 1/2 times -9.8 is going to be -4.9. And we do have one equation with one unknown. What does this look like? It sure is a quadratic. So if you want to solve this the easy way, you have to use a quadratic. Hopefully you've got the thing in your calculator where you can just plug those values in. -4.9 would be your A, -5 would be your B, +150 would be your C. But if you're like me and you have a little scientific calculator that does not do quadratics very easily, that's just fine because we've all got smartphones. And there are about a zillion apps that have quadratic equation things on it to solve. I use something called Show Your Work Quadratic Formula, and you just type in the numbers into this. So I just put in -4.9 for A, -5 for B, 150 for C, and it spits out two different answers. One answer is 5.05. Another answer is -6.07. So the answer that you should pick here is 5. Exactly. Time is not a negative thing, so we're going to go with the positive value. So yeah, the answer would be 5.05 seconds. Now it's kind of interesting, the alternate answer, that 6.07, that is going to be if we were throwing this up at 5 meters per second. If we were throwing it upwards, it would take longer to hit the ground, and that's where that answer would come from. Kind of a neat little thing there. Now there's actually an alternative way to do this problem. Because let's be honest, when I started teaching here, I did not have a smartphone or a graphing calculator. So how did I do this? Well, as I said before, in this section, sometimes you can do the same job with different tools. So instead of using this equation up here, let's take a look at these. I've got time right here. So if I want to solve for time, I could just isolate the t. So I'd move velocity to this side, so it'd be v minus vo. And then to get rid of the a, yeah, divide both sides by a. So my time would be equal to v minus v original divided by acceleration. Now I know acceleration, that's negative 9.8. Original velocity is negative 5, but I don't have the final velocity. But I can get the final velocity using this guy. So my original velocity again is negative 5. Acceleration, negative 9.8. It's always going to be that as long as we're on Earth. What is our change in height? Negative 150. So, if I want to get this v so it's not squared, I got to square root both sides. So I'd have this. And if you plug that into your calculator, let's see what happens. So I'm getting 54.5. And because I'm going down, I'm going to set it equal to negative. Because remember, when we take the square root, the result can be positive or negative. You can pick. And because we're going down, I'm setting it equal to negative. So now I have everything. So let's plug everything into that equation and wonder if we get the same answer. So v is going to be equal to final velocity, which is negative 54.5, minus original velocity. So this is going to be minus negative 5. Yep. Oh, yeah, you're right. Thank you. And boy, wouldn't that be something if this came out to be 5.05? And so you get the exact same answer, no matter which way you choose to do it. So what this means is, if you're using an equation, you get an answer, and your friend's like, I used a different equation. Don't assume they're right. There could be more than one way to do that problem, and there probably is. Most of these problems, there's more than one solution to it. So, there you go. I thought that's kind of interesting. Something else that is interesting is we've been dealing with free fall so far. And free fall is kind of a neat thing because, you know, this is why I really enjoy physics so much, is because it's the real world, you know? You don't need a microscope or a telescope or fancy chemicals to do physics. You can actually figure out how high up you are anywhere simply by dropping something and timing how long it takes to hit the ground. If you look at this equation, y equals y original plus v original t plus 1 half at squared, if you're dropping something and you see the impact location, let's just see what happens here. If you know that there's an impact spot, final height will be 0. Original height is probably what you're looking for. If you just let it go and don't throw it down, original velocity goes to 0, so that whole product goes to 0. And that's what we have for the rest of the equation. Of course, this is negative 4.9. So when I move this to the other side, it becomes negative, and then the negatives cancel each other out. And we have this beautifully simple equation that just tells us how high up we are if we drop something and time how long it takes to hit the ground. So if you time something, you just put the number here, square it, multiply that by 4.9, that's how many meters you're above the ground. And of course, we don't usually deal with meters, we deal with feet. And so that's just a small adjustment. It'll just be multiplied by 16. I used this not long ago because My dad is actually friends with the guy who runs the giant clock tower in one of the old Catholic churches up in Oshkosh. And so we were up in the clock tower seeing how the whole thing works. It was super interesting. And there's a spot where you can look down and you can see all the way to the ground floor of the church. And so we're all kind of wondering how high up we are. So me being Mr. Physics, I just dropped something and timed it, plugged it into this equation, found out how high up it was. So it's kind of a neat little thing that you can do, and it's nice and simple. You don't have to have this written down to figure that out, 16t squared. Beautifully simple. That's what physics is all about. Okay, so we're going to take a few notes today, get something out to write with, something to write on. I wonder if I can make it look like the shark is eating me. This is tough. There we go. I'm officially in the shark's mouth. Not that you guys can tell. You have to watch it sometime. Okay. So, we've been talking about things in one dimension, either vertical or horizontal. Now we are going to make the transition to 2 dimensions. Because let's be honest, when something is flying through the air, chances are it's not going straight up and down. It's probably going in some sort of arc. And that's what we're going to discuss a little bit today. So, let's think about this for a second. I've got my shark here. I'm going to load him up with a special shark pellet. And when he launches, it takes a certain path before it hits the ground. Yeah, exactly. It goes partially horizontal and then it curves down. So we need to, if we're going to analyze 2-dimensional motion, we have to analyze them separately, at least in the beginning. So let's do that. First thing I'd like you to do is draw a nice big line kind of down the middle of your piece of paper. It doesn't have to go all the way down, maybe halfway down your page. Label the left side horizontal and the right side vertical. Now we're going to ignore air resistance here. So when I launch this object from the mouth of the shark, it takes a certain... Oh, did that go in?
Yeah.
Oh my gosh, that is awesome.
Who recorded that? Come on, guys. Let's clap for Mr.
I'm out.
I mean, period.
He's gone.
He's gonna come back. And then it's so. That's not. Bro, you're wasting M&Ms. So how's everybody's day? Who wants some M&Ms? Hey, hold on. Hey! Those are my M&Ms, bro. Why you saying what? I mean, girl, come on. I did not deserve those. Yes, I did. I'm just kidding. I just choked up. We're not gonna give you a share for. Hey, at least she's not wasting them like you. They're all over the floor. I didn't waste it. 2, Tati. That's 2 M&Ms. How's everyone? Oh, where'd you go?
Felt a little bit like a rebel out there without a mask on.
What'd you do?
I just fucking got a drink.
Okay.
So, we've got 2 things we need to consider in this type of motion. We've got horizontal and vertical. So remember we talked briefly about motion maps. I just want to show a little bit about what's going on with the motion of this object as it goes through the air on its path to the ground. Horizontally, what forces are acting on that object as it flies? We're going to ignore air resistance here. So just horizontal forces. Do we have any?
Wait. Once it's in the air?
Yeah. No, exactly. No horizontal forces. So what that means is that as this object is going through the air, it is not slowing down horizontally. It's continuing that velocity. So its horizontal motion map would just look something like this. You've got arrows that are the same length. They're not getting bigger or smaller. Those should be the same length. And which of Newton's laws does that remind you of, that an object in motion will naturally stay in motion? Newton's first law. Just write down Newton's first law. You got to give him credit. Now, in terms of an object that's moving, where it does not accelerate, where it has the same speed the whole time like this, what equation do we use to figure out position? It's not up here. Anybody remember what it is? It's a real short one. Yeah, x equals vt. Because if we're looking for the position of an object when it's moving without an acceleration, this is the equation we're always going to go to. For horizontal motion with no speeding up or slowing down, this is what we're going to do. So that's the horizontal portion of this object's motion. Let's take a look at the vertical portion. Vertically, as that ball is, I suppose I should do it again. As this flies through the air vertically, oh, it got in the way. That might have had a chance. What's going on vertically with that? Just gravity. So if gravity is the only thing that's acting, it's going to be speeding up going down because we've got that force. So the motion map for that would just have arrows that are growing in size. Anybody remember which of Newton's laws says that when you have a force, you're going to have an acceleration? Newton's second law. Very good. So let's give Newton credit again. Now, which equation are we going to use to describe the position of an object when there's an acceleration? This one is up there. First one, yeah. If we're describing the position of an object when it's accelerating, we use this. So again, before we go further, I want to make sure you realize that horizontally, this object is not slowing down. It continues with the same horizontal velocity the entire time it's in the air. Vertically, though, it's picking up speed going down, which oftentimes gives objects the illusion of slowing down because they kind of arc down like that. They're not slowing down, they're just speeding up vertically. That's why it looks that way. Horizontally, it's still moving the same speed the entire time from beginning to end. Now, here's the thing. If we're talking about two-dimensional motion, there has to be some connection between these two equations here. Any thoughts on what might connect this equation with this one? Say it louder. Time, absolutely. If we can use this equation to figure out how long that object is in the air, we can use that to solve for horizontal position over here. So time is the way that we connect these two equations. Make sure you know that. Make sure you know that time is shared between those two. Something else that you do have to be aware of before we try a problem with this is because, see this x here? This means it's a horizontal equation. So what that means is that when I look at this velocity, this is going to be a horizontal velocity, not a vertical one. Over here, because this is a y, I automatically know I'm dealing with things vertically, which means this is a vertical velocity. This is a vertical acceleration. So you have to make sure that you remember that. And as we practice, hopefully you'll get better at recognizing it. When I was a student teacher 11 years ago now, my supervising teacher had all of her students, for this equation, write down that this was Vy original. So they remembered it was vertical, and this was acceleration in the y direction. And they had to put a subscript next to this V, which was an x, so they remembered it was horizontal. I'm not going to make you do that, because I think it's cleaner this way. But the thing is, you do have to remember that when you're dealing with this horizontal equation, everything inside of it is horizontal. When you deal with a vertical equation, everything inside of it is vertical. And you'll see that in the next example. Questions so far? Okay. He'll be good there. Come on. Okay. All right, here's our setup. Go ahead and draw this in your notes. Yep.
Okay. What do you think it was? LM? 1 mile.
So here's our setup. And again, we're taking a huge step forward here, because now we're not just dealing with things rolling on a flat surface like in velocity and acceleration. We're not just dealing with things falling vertically like we did on worksheet 1. We're combining these two. And so it's going to get a little bit more complicated, but see if you can hang on to your seat here. So the setup is, we've got 5 meters per second. That's the speed this object is rolling off the table with. And then it falls and it hits the ground a certain distance away. The table is 1 meter tall, which is about the height of the tables in the back. So the question then is, how far away from the table is this object going to land? So, this is a horizontal distance that I'm looking for. In addition to these equations here, you got to make sure that you're aware of this one, because we'll be using that a lot for our horizontal motion. Because again, horizontally, this object is not changing speed. So if I want to find that horizontal distance, I just use that equation. X equals vt. My velocity is equal to 5. My t is equal to O. I don't know my t yet. So we got to figure out what that time is. Which equation you suppose we ought to use to do that?
We got 5. Oh, we got to use the Y one.
The y one, absolutely. Because this equation's not going to work because we don't have time in there. So this equation's not going to work because we don't know what the final velocity is. So the only one that has just one unknown is this guy here. So we're going to use this equation to find time, and we're going to plug that time in to that equation. All right, I know my impact spot. So what is my final height?
0. Wait.
0, yep. It takes a while to get used to. What's the original height? Yep, 1 meter. Then I've got original velocity. What's my original velocity?
0.
Why?
I don't know. I just thought it would be zero because
You're right on the money. You are right on the money. And the reason you're right on the money is because this is a vertical equation. 5 meters per second is a horizontal velocity. Vertically, this object is not being thrown down or up. So vertically, the original velocity is a straight up 0. So this is 0 right here. Yep, plus 1/2 AT squared. Yep. So let's see, I got to put the 1 over here. That'll make it negative, and that negative cancels out with this negative. That's 4.9. Well, when I move the 1 over, it becomes negative, and then that negative cancels that one out. You have no cavities? That's awesome. Me too. If I could, I'd give you a high five. But I think that's illegal this year.
not illegal. I don't really care.
So when you do this all, your time is going to be equal to the square root of 1 over 4.9. Anybody calculate that?
And all the healthy people get off cavities.
0.45.
Very good.
2, 2, and 1. Are we keeping track now? 0.
So we have our time. So if this is our time, keep it down a little bit, ladies. Thanks. So if this is our time, all we got to do to finish this up is take it and chuck it in right here. And because we already know the horizontal velocity, that's 5. I just got to go 5 times 0.452, 2.26. So my horizontal distance is 2.26 meters. And that's how you do two-dimensional problems. Generally, it's just a matter of using this equation to find time, and then use that to figure out something horizontally or something else that they have in mind. Yes? Like, oh, these two? Yeah, you could. There's still scenarios where you'll use those. Yep. So yeah, vertically, even though this object is moving horizontally, vertically, it's still going down at the same rate as if you would just let it go. And it'll take the same amount of time to hit the ground. That's actually something that we're going to look at in terms of Mythbusters. We don't watch the full episode, but they have an episode where they drop a bullet at the same time that they shoot it horizontally out of a gun. And they actually hit the ground at the exact same time. So, even though this object is moving horizontally, that does not make it hit the ground any faster or slower. Questions on this? Okay.
How long is the worksheet?
It's just 1 page, 2 sides.
That's not pretty long.
And this is going to be due on Thursday.
Alright.
And I'll even get you off to a pretty good start here.
First page? That's fantastic. The whole first page?
What's that?
The whole first page?
No.